Chiara already mentioned this contract, and I will go into more detail on it. Essentially, it's about developing an operational service for the water sector, and we are looking at several different aspects here, but I will focus mainly on the EURO-CORDEX projections and how we work with them for the climate part here. So the aim of this so-called sectoral information system is to help a broad range of water managers in the fields of, for instance, water allocation, flood management, ecological status, and industrial water use, and to help them adapt their strategies for seasonal outlooks, and in order to mitigate and adapt to the effects of changing climate. To this purpose, we're looking into climate impacts as well as hydrological seasonal forecasts. We produce different data sets. We produce Explorer applications to go along with the data sets and accompanying user guidance. We are also working with users to construct showcases using our services, and they will be promoted as practical examples for how to use the new data that we ingest in CDS, and work as tools to inspire other users to get started with climate adaptation. In this rather complex schematic, you can see the data flows within the contract. We have the CDS climate data store to the left, and where, for example, EURO-CORDEX sits, and the seasonal forecasts, and the reference data set we use. And we use the climate data store to, we extract data from the CDS, and then we process it further offline with our tools for bias adjustment, for example, and run our hydrological impact models. And then we produce seasonal forecasts or climate projections and ingest them into the CDS toolbox again. So for the climate applications, we're at the top of this schematic, and there's always this user feedback when setting up this the setup, what we produce, and it comes to a large extent from previous proof of concept contracts. And after we have applied the hydrological impact modeling, we also produce climate impact indicators, which are, for example, changes in 30-year means or in different extremes and so on. And we ingest them into the CDS toolbox to give easy access to get a quick overview for users on what's happening within the sector. So the EURO-CORDEX data that we use, first I should mention that for hydrology, we have difficulty in using global climate model data because of the large grid structure, coarse horizontal resolution. It is causing issues with when we are routing water across the continent, especially along larger water dividers. So we really benefit from the high resolution of EURO-CORDEX, and we're looking here at the 12.5 kilometer simulations. We have specific criteria that needs to be fulfilled for the models that we introduce in our contract. The first one is that they must cover the complete time period, 71 to 2100, which most of the simulations do. We also need or want to have all the three RCPs, 2.6, 4.5, and 8.5. This has been somewhat limiting the ensemble that we can have. And most importantly for the hydrological model is that we need to have the necessary forcing data to drive the hydrological models. So from the two models that we use, EHYPE is not so sensitive to this criteria, as it requires only daily mean temperature and precipitation, so which are standard outputs from all models. The VIC model that we use needs precipitation, temperature, but also humidity, radiation, wind, for example, all at 6-hour intervals. And this is not doable, and as these outputs are generally not available. Still, we use disaggregation, statistical disaggregation from daily scale down to 6-hour data, which increases the number of ensemble members possible. But it still requires that the correct output data exist at least the daily scale, or relevant variables, so we can derive some variables. So what you see in the table here is the final ensemble that we have used in the contract. And at the time that we started this work in 2019, this was the largest ensemble that fulfilled all the criteria. There was one more model, but it was removed for some error in the processing. And so this is clearly an ensemble of opportunity, as we say. It's not built from the purpose of balancing climate uncertainty, as Chiara mentioned. And it would today be possible to use a larger ensemble for these purposes. And in the next step, we use bias adjustment, as Chiara also mentioned. And the reason is shown quite clearly here. This top figure shows a random grid point in Central Europe. The temperature distribution over a 30-year time period from daily data. So we see here we have the black line shows the observational data that we use from EFAS-Meteo, and it shows a clear bimodal peak, bimodal distribution with a summertime and a wintertime normal distribution overlapping. And then we see in the different colored lines the different RCM-GCM combinations that we use in our ensemble. And we see that they deviate quite strongly with a generally too cold temperatures over this area and in general over Europe. Also, if you look at freezing temperatures around 0 degrees, there is quite large bias in different models, and this can have large impacts on hydrology, as it determines whether the precipitation will go directly into runoff and discharge, or if it's stored in snow or ice, and to give later impacts later in the year. Therefore, we apply a bias adjustment to be able to run our models, which have been calibrated towards this reference data EFAS-Meteo. And we use a multi-time scale quantile mapping method. What that means is that we are looking to the complete distribution, such as shown here, and we adjust the models to look more similar to this distribution. This is not done on all the data as we see here, but it's done at a monthly scale, so essentially normal distributions. And the time scale part means that we are not only doing this on daily data directly, but we do it separately on 31-day averages and on daily anomalies from those averages. And that's a way to separate bias that can be different at different time scales, and to avoid what's called the inflation of variance issue, which means if the model is underestimating the variance, for example, then if you try to force it into looking at to have a larger variance, it can have a quite strong effect on the climate change signals. So this is a way to reduce this impact. The bias adjustment is also very dependent on the reference data used. We use EFAS Meteo here, which is a 5-kilometer resolution dataset used for the EFAS hydrological forecasting system. So it was chosen because it fulfills several needs within this contract, and some of them being for the seasonal forecast, we need to have real-time updated datasets for the forecasting part. And that's why it's a bit unusual reference data set compared to the ones that Chiara showed, EOBS and the WFD-E5 dataset. So the next step, now we have our forcing data, now we want to apply it to our hydrological model ensemble. And then we have two different model systems or concepts. One is the distributed hydrological model HYPE from SMHI, and then we also have the macro scale model VIC from Wageningen University and Research. The eHype model is applied in two different setups. One with its normal setup, which is on catchment delineations, so polygons rather than gridded regions. And we have somewhere over 35,000 catchments within Europe. In order to explore model uncertainty here, we set up this model using different parameters. So we have different calibrations of the models, let's say. One is the standard operational model that we use, adjusted to reference data. And then we have a parameter perturbed model in a semi-automatic calibration strategy, and tuned by performance in the hydrographs, but also to give a range of parameters. The second ensemble consists of the two models eHype Grid and VIC-WER, and they are set up on the EFAS drainage network instead. So the 5-kilometer grid following the same grid as the EFAS Meteo data we drive the models with. When we look into climate impacts, we use two different approaches. One is the time slice approach, where we divide the record into 30-year time slices and calculate absolute or relative difference between different time periods. Pretty much the standard approach. But we also look at what's called degree scenario approaches, where we look at 30-year time periods when the GCM, the driving GCM, reaches a global mean temperature increase from pre-industrial conditions by 1.5, 2, or 3 degrees above, above the pre-industrial condition, to stay closer to different political targets, as for example the Paris Agreement. And here we don't have a fixed future period, but it's different for each driving GCM. And you see in the table here, and the differences here relate to many different things, as Chiara mentioned, but one of them being climate sensitivity of the models. And then, as I mentioned, we compute climate impact indicators based on this. So we have some meteorological ones relevant for the water sector, mainly temperature and precipitation-based ones. And then we have a larger set of hydrological indicators, such as many relating to river discharge and mean or extreme conditions. But we also have runoff, soil moisture, and different drought or aridity indices. And for the eHype catch models, we also have water quality indices, such as the water temperature and nitrogen and phosphorus load or concentrations. So these data have been ingested for eHype catch, and the gridded models are being ingested now, and the first dataset on the catchment models will be published soon. And we have started to build an Explorer application to look at the data and explore them online. So this is now under review. So it will also be soon available, the first version based on the catchment models and climate models. And here, for example, you can go into the menu system and select different variables, ensemble mean or single models, different time periods, and different emission scenarios. The degree scenarios will be added later. And the map is interactive, so you can click a grid point or a catchment, and it will display a graph with more detailed information, such as single climate model results, median, quartile information, also multiple hydrological models, if that is applicable. The default maps shows the ensemble median change, and in this case I show here, it's for precipitation based on the EURO-CORDEX ensemble and without bias correction, just regridded to 5 kilometers. But we also show the bias adjusted results. Here with very similar change pattern. There are some modifications to the change signals. And we show then also, here's the change in mean river discharge. And for example, we can see that compared to the precipitation signal, the discharge can deviate somewhat. So in, for example, the point clicked here in eastern Sweden has a mean increase in precipitation. And when it comes to discharge, it's not as clear. And in eastern Sweden, the relative wettening from the precipitation signal is turned to a relative dryening in the discharge, because the competing processes between increased precipitation and increased evapotranspiration. Looking into extremes, here the 50-year return period of river discharge, we can also see that it's a much more heterogeneous pattern, and of course the uncertainties increase a lot when you go into these extremes. But we can get a feeling of what will happen in the near future. And here I just show a zoomed in version, so you can see the catchment delineations and the scales we're working with here. And the example shows the I think, yes, the nitrogen concentration in catchments. And here you see that the different modeling systems shown in the box plots above, the EHYPE catch, the operational model, and the perturbed physics model ensemble is they deviate quite strongly for this variable. So to conclude, we benefit a lot from the EURO-CORDEX type model ensembles, as we need this very high resolution for the hydrological impact modeling. And at the same time, we'll need large ensembles for when addressing robustness in climate change projections. So we welcome very much this extension of the EURO-CORDEX model ensemble, and recommend future continuations of our current contracts to include more models in the hydrological ensemble as well. And we also recommend increasing the hydrological impact model ensemble, since there is another layer of uncertainty from the hydrological models. And I also want to stress the user inputs for developing applications and user guidance, and to make our data outreach as useful as possible to really promote actions on climate adaptation. With that, I thank you for your time.